Okay, we're a few minutes past the hour, but I think all the pieces of technology are now set up and working, so we can go ahead and jump on in and get started. So thank you, Giannis and Danny, for the invitation to be here today and talk about some of the science that I do. At the moment, most of that is JWST science, but I actually won't be talking about JWST today, except the little bit that I do. What I will be talking about is the Sloan 4 MaNGA survey, which was a large-scale IFU galaxy survey that I was involved with for the best part of 10 years or so, wrapping up observations about 4 or 5 years or so ago now, and tell you some of what we've learned from that in terms of understanding the turbulence of the ionized gas in galaxies. And because I just can't give a talk without talking about JWST just a little bit, there'll be a few slides right at the end on some particularly cool things that we've done lately, looking at massive stars with Webb, and some of the very unexpected things that we've learned from them. So mostly I'm a galaxies person. I focus mainly on galaxies in my research and answering a variety of different questions about those galaxies as the fundamental building blocks of structure in our universe. So at the very largest scales, then you can ask things about how do galaxies themselves en masse form? How do they give rise to the structures that we see in these galaxies? How do we see spiral arms, the Hubble sequence? How do they grow and merge to form ever larger systems? But if you look from the bottom up instead, then it's really an exercise in star formation. How do stars form in galaxies? How do stars get their gas? How do they give rise to the metals that we see in galaxies? And ultimately, what shuts down that star formation, turning very blue star-forming galaxies into very red galaxies that are more just passively evolving and merging without much in the way of ongoing star formation. And it's that latter that I'm going to focus more on today. A lot of what we know about the star formation in galaxies is based on spectroscopy. Spectroscopy is how you get the physics of star formation. And much of what we've learned from spectroscopy of galaxies is from very large-scale, statistically large surveys, such as the Sloan Digital Sky Survey, things that get spectra of millions and millions of galaxies, like this one that you're seeing here. So state of the art as of about 15 years or so ago was that you take an optical fiber, you plop it on the galaxy, you get a spectrum of that, and that gives you everything we know about the galaxy in terms of its metallicity, its star formation rate, its history, whatever kinematics are in the galaxy, whether or not there's an AGN at the core. But you can see just from the figure that we're looking at that that little blob in the center is not necessarily terribly representative of the galaxy as a whole. It's probing the very center of the galaxy, and it's not telling you about the wealth of information towards the outside and the actual star-forming regions themselves. We can do a little better if you use slits instead. If you put a slit like that across the galaxy, you get a bit more representative. You get information from more parts of the galaxy, but it becomes a lot more difficult to do such large statistical studies of galaxies with such things. What we really want to do instead is take an observation that looks like this, where you've packed those fibers in and you get spectra everywhere in a different galaxy. That's now the state of the art as of the 2020s, and that is the result of a lot of dedicated work over the course of the last 10 to 15 years or so. We can take those kinds of observations and make maps like this. So you can now ask, where is the star formation in that galaxy? Well, you can see there's a giant ring of star formation here, and you can trace those tidal tails. How old are the stellar populations in different regions? In this case, it's old in the middle, it's younger towards the edges. How is the galaxy rotating? What are its kinematics? What are the gas and the stars doing? There's a wealth more information when you have spectra all through a galaxy than just when you're looking at one single non-representative part of the galaxy. So that's the idea behind integral field spectroscopy, which many people here are probably already familiar with, as there are many different instruments that use this technique now. Basic idea is that you chop up your galaxy, or whatever other target you're interested in looking at, into lots of different pieces, disperse the light from each of those pieces, and then reassemble them into some kind of a cube of data across the entire object. How you chop it up is, there's a variety of different ways you can do it. In this particular example, it's an image slicer, so lots of little slits all next to one another. For surveys like MaNGA and others, then it's optical fibers instead, where you pack fibers together and you disperse the light through those optical fibers instead. So I actually came to this from the high redshift universe. I'd got involved with doing what was then high redshift galaxies, redshift of 2. It sounds very passé now. But we were involved in doing high redshift galaxy studies with IFU and slowly working on understanding the very origins of first galaxy formation by putting together samples of 2, 10, 20 building up those samples of tens over time, and eventually others joined in. We've now built up samples of hundreds of galaxies at high redshift, now pushing even to redshift of 6 through 8 or so. But we really didn't have a good understanding of our low redshift local universe that we could compare to. We couldn't ask, when we see something unusual at redshift of 2, is that actually unusual? Is it different about galaxies in the young universe? Or is it just something that we see today if you look in the right kind of environment? So the landscape of redshift 0 IFU studies was beginning to develop at that point in time, but still severely limited in many ways. So early on, you had things like the Atlas 3D survey from Michele Capellari, Eric Amsalem, and others that looked at a sample of a few hundred or so early type galaxies, but didn't really touch the star-forming sequence. You had things like the Khalifa survey from Sebastian Sanchez and others that put together about 500-600 or so galaxies of various different kinds and taught us a lot, but wasn't really statistically representative at the level that we'd like to be. And a variety of others in there as well, filling in certain different kinds of galaxies with a few tens or a few hundreds or so. But this lack of large-scale surveys is what motivated two surveys, both the MaNGA survey that I'll talk about today, getting about 10,000 or so galaxies by the end of the survey, and also the SAMI survey, which was pretty much cotemporal with MaNGA, doing a very similar thing, observing about 3,000 or so galaxies with a slightly different spectral and instrument setup, but aiming at some very similar goals. So MaNGA itself stands for the Mapping Nearby Galaxies at APO program, an acronym that is only very slightly contrived to reflect the fact that our PI lived in Japan at the time, and we wanted something that would give us good reason to come up with entertaining comics that we could show in various slides while we were doing our presentations. So our PI, as I mentioned, is Kevin Bundy, who's now at the UC Santa Cruz, and a large number of other people from institutions across the world who joined together in the Sloan Digital Sky Survey's 4th iteration to bundle the fibers from the previous spectrographs. These are the BOSS optical fiber spectrographs that have been used for baryon acoustic oscillation mapping in the young universe. And we bundled them together to do galaxy science instead. As part of this, and we built about 17 pluggable IFU fiber bundles for multiple different cartridges with a range of numbers of fibers from 19 all the way up to 127. We packed them together to build IFUs like this in these pluggable steel ferrules that we could plug into each of our plates to observe where we wanted to on the sky. I'll show you what that means in a moment. Gave us a spectral resolution of about 2,000 or so and a coverage of the entire optical waveband plus a little piece of the near-infrared going out to about a micron or so. And we had pretty much nightly observations for the best part of 6 or 7 years. So it took a while to build up the survey, but certainly we had a very large fire hose of data providing us information for many years that we could work on reducing and building into our large sample that we wanted to eventually put together. MaNGA, as I mentioned, uses plug plates. For anybody who's not familiar with the Sloan plug plate system, then these are large aluminum plates about this size or so in diameter, where the idea is that you know where you're going to be looking on the sky ahead of time, and you pre-drill holes in those plates at the exact location of the targets that you want to look at. Sloan's been doing this for single fiber spectroscopy for years, and we adopted the same technology for the IFU bundles that we wanted to use. We designed a few thousands or so of these plates, designed them with the holes that we wanted to look at with our IFUs, and then each day you mark up those plates with what has to go in what hole, and pluggers, in this case our fearless PI, plugs each one of those individual optical fibers into each one of those holes, which sounds really tedious, but turns out to be remarkably efficient. You do this in the daytime with about 6 or so of those cartridges, and in the night, you wheel them down to the telescope, load one up, observe for a couple hours. When you're done, drop it out, load the next one in, and keep going through the night. And we did that for about 6 years or so worth of data. And here's just a couple of scenes from the commissioning of it, along with all of us starting to dig into the very first data that we were starting to get off of the telescope. It was a really fun time being at the observatory when we got that project started. So MaNGA is foremost a galaxy survey. That's what it was really designed to do. By the end of the survey, we'd observed somewhat over 10,000 individual galaxies, ranging from redshifts of about 0.02 to 0.15. So local universe, but going out a little further so that we could get a statistically representative sample. I'm showing you here a distribution of the star formation rate and stellar mass for the galaxies. So stellar masses of about 10 to the 9 through 10 to the 11 or so. star formation rates that pick up both star-forming main sequence, the green valley, and also the red cloud of elliptical galaxies as well. Two different kinds of samples, a primary and secondary sample at slightly different redshifts. The aim here to go out to slightly different radii in the galaxies, either 1.5 or 2.5 effective radii, depending on what exactly the science focus was. There are a bunch of other pointings in there as well, weird stuff that we tossed in over the years. Some looks at Andromeda, some looks at IC342. We looked at the coma cluster, intra-cluster light, a variety of other things as well. So there's other stuff that we tinkered with, but galaxies is really where we were focused. Was also, however, a stellar library. If you want to look at galaxies, that's harder in bright time when the moon is up and blasting you in the optical. So what we did with our bright time is we turned it into a stellar library. The best thing to do with an IFU is generally not to take a giant 30-second IFU and look at a single point source right in the middle. It's a terribly inefficient way of using it. But if it's otherwise going to sit idle, it turns out to be a useful thing to do. So one of the problems that you often face in analyzing the galaxy spectra is how to come up with good stellar population models, how to model your galaxy light and break it down into the light of the individual stars that go into it. And you're always faced with the problem of how do you match the characteristic of your stellar models to your galaxy observations. Either the wavelength range is different, the spectral resolution is different, you don't have quite the coverage that you need, etc. Because we were doing this, we had the freedom to design and build our own stellar library with exactly the same wavelength coverage, exactly the same spectral resolution, and fill in all the parts of parameter space that we thought we needed for our analysis. So over the course of the survey, we actually observed over 26,000 stars or so with a signal-to-noise of greater than 100. I'm showing you a couple examples here at the bottom, all the way from the very hot O dwarfs down to M giants, M dwarfs, and even a few Wolf-Rayet stars that we had in there as well. So even though this was just by the way, we should do something in bright time, we ended up building up a stellar library that was substantially larger than the MeLS library and has been useful in its own rights even after the survey's finished. I'm not going to go into much detail on that, though. Today I'm going to focus on emission line physics and what it can tell us about star formation in galaxies. When you look at a typical spectrum of a bright star-forming galaxy, you'll tend to see something like this, where you see a little bit of the stellar continuum at the bottom. In this case, you might see the 4,000 angstrom break. You also see lots of different emission lines from H alpha, O3, O2, lots of different low ionization species arising from the star formation regions in those galaxies. These are the things you see if you look at HST images, the bright star-forming knots and things like M83. If you look at nebulae such as this one, these are the bright lines that you see in those. And they tie together star formation from the low scales when you're looking at individual star-forming regions, all the way up to the scales of the galaxies that we're looking at. One of the common ways that you can try getting information out of those emission lines is by looking at emission line ratios. So because each of those emission lines is produced by gas that's been ionized in a slightly different temperature, a slightly different degree of ionizing radiation, they trace gas in slightly different areas. Things that have been photoionized by a relatively soft or hard ionizing spectrum that can tell you about the sources of ionization, be that either stars, be that AGN, or various other things. This is something people have done for many years, and most of you here are probably already familiar with to a reasonable degree. This is the so-called BPT diagram, where if you take ratios of those lines, like say oxygen 3 to H beta, nitrogen 2 to H alpha, you can make plots like this that show the main star-forming sequence, and also a spray up here due to either old galaxies or Seyfert-type galaxies. And much of this information here was pinned down by the early generation Sloan Digital Sky Survey. This is what we got from the single fiber information for statistically large samples of galaxies. And that's what we're going to be adding on to here with the MaNGA survey. In particular, one of the things we'd like to ask is whether or not galaxy kinematics can help us improve those classifications, both the classifications observationally into which galaxies are star formation ionized and which are driven by AGN, but also help bolster the theory that goes into understanding how each of those regions are formed. The idea behind it is that galaxies very roughly break down into this kind of structure for a star-forming galaxy. You have some kind of a old bulge in the center. You have a disk outside that, a very thin disk in which you actually get your molecular gas and new stars forming today. and an older thick disk in which your older populations of stars live. This has a higher scale height, both because there's been more time for those stars to scatter up to larger velocity dispersions and scale heights, and also because as you look back in history, then the stars themselves seem to have been born with intrinsically larger velocity dispersions when you look back to a redshift of 2 or so. So what we should see when we look at these kinds of observations is that we should be able to actually pick out by the kinematics we're looking at which population of stars we're looking at. When we look at the star-forming sequence, we should see the cold disk. When we look at things around AGN or older populations, we'll be able to see the kinematics of the larger scale heights. We've got a good indication that we might see something like that. So there's some indications from various early works I'm showing here, where if you start looking at the star-forming sequence, in these couple examples they've looked at, they do indent to have lower velocity dispersions, higher velocity dispersions, the AGN region. If you plot the velocity dispersion against these line ratios, then as you go to larger line ratios, you go to larger velocity dispersions, suggestive that we should be able to help fill in this diagram. And we do, with statistics that are really on our side now. So instead of the previous observations where there's maybe a few tens of different individual observations we're putting together, here with MaNGA, then we can provide robust measurements of the velocity dispersion for about 3.5 million independent pieces of over 4,500 individual galaxies, and really fill out that plot. And we can now say, if you look at these kinds of line ratio diagrams, how the typical velocity dispersion behaves as a function of where you're looking in that diagram. We can see very clear divisions between these different regions. If you look in the star-forming sequence here, then you see very obviously that is the place that you will get these cold disks. That is where you get your 20 kilometer a second dispersions from the star-forming disk. As you look up to the more AGN and linotype regions up here, that's very clearly distinct. You're seeing a different dynamical population with velocity dispersions up to more 100, 150 or more kilometers a second. Each one of these points that we're looking at here is just an average of all of the spaxels across all of these galaxies that are going into that point in the diagram. But there is, of course, a width to that distribution as well. Here's what you get if you break it down in terms of the width, where if you're now looking at things color-coded according to their distance from this plane. So if you draw this dividing line here between the star-forming and the non-star-forming sequence and plot either the distance to the left or to the right of that line, you can really break out what those different populations are. You see that there's a very cold sequence here, peaked at about 20 or so kilometers a second, which is where your star-forming disks are. And there's a much hotter and also wider distribution extending to 100, 150 kilometers a second or more as you get further and further away up from that line and ionized by more exotic mechanisms than star formation. Those gas kinematics allow us to revise the classification boundaries that we had before, now that we've got a more representative set of measurements across a wide range of galaxies. So I'm showing you here 3 things. So there's 3 different ways of measuring line ratios, either the N2, the S2, or the O1 line ratio. They each tell you slightly different things from slightly different elements. I put a classification scheme up top. This is by and large a known and established classification scheme. All we've done is revise the boundaries somewhat. In the middle here is the density distribution. So what is the number of points that we've observed at any different location in a galaxy? Obviously, they cluster most around the star-forming sequence. There's a lower density of points up here, but nonetheless still hundreds to thousands of individual points. And then at the bottom, I'm showing you the velocity dispersion we observed, the H-alpha line width, where you can see that we've been able to revise these classification schemes slightly to follow better the contours of what the actual dynamics in the galaxies are doing. When we do that, we can find that we match trends in a lot of different ways. So I was showing you previously the gas velocity dispersions. You can also look and see what the stars are doing instead. So the stars and the gas in galaxies have different kinematics. They behave in different ways, but nonetheless, they trace similar regions in this diagram. So if you look now, I'm showing you the stellar velocity dispersion on the top with the same lines from the previous figure. You can look at it and see in star-forming disks, then you get similarly comparable velocity dispersions between the stars and the gas, although there is some offset between them, of course. The gas tends to be colder than the stars. As you look up towards the AGN type region, then you start to see that the velocity dispersion of the stars can be considerably higher. You're tracing a different phase of the gas. And as you look towards the older regions of galaxies where there isn't much new star formation, these older stellar populations, and the velocity dispersion in those regions is significantly larger. You can do this for a host of other properties. Because we've got full spectral information, we can make measurements of many different quantities. You can now say, now, how does age correspond to these things? Measured either according to the equivalent width of H alpha or according to the strength of the 4,000 angstrom break. And you can start reading off information from these plots. In this case, well-established trends, but things that you can now just read easily from these plots. You can see, for instance, that these lino-type galaxies in this region here have old stellar populations compared to everything else. Star-forming regions, of course, have young stellar populations, whereas AGN prefer intermediate-age stellar populations. You can look at the radius of where this emission occurs. By and large, star formation is tending to occur at larger radii in galaxies. Star formations occurring further out in disks as they grow. Whereas when you're looking at AGN, they're concentrated more towards the middles of the galaxies, likewise with the older stellar populations. You can do the same thing with the overall galaxy stellar mass and see that the older populations occur in the most massive galaxies where you get these lino-type line ratios. And you can even read off the mass-metallicity relationship from this plot as well, based on the trends along the star-forming sequence. So far, this is all just telling us things that we already knew, but it's a particularly powerful way of looking at the information where you can see how it populates these regions of emission line physics and compares the ionization mechanism of the gas to the things that you can measure from the individual spaxels themselves. There's a complication here, of course, that you can look at plots like this and see there's this region in the S2 diagram of yellow populated in the blue. The reason why is because if you look at the actual physics that goes behind the grids of the models you make for these, those grids are not constant. They fold back behind one another in a complex space so that you can end up with multi-valued information. If you just look at something in this region of parameter space, you can't necessarily tell if it's just a star-forming galaxy or if it's something that's older instead. So as part of a project they did with Renmin Yan and his postdoc Jihan Ji a few years back, you can come up with ways of reprojecting all this information into a more complex space, put together the information that you know from multiple different emission lines, and find a way that you can break those degeneracies and come up with something that's a lot more linear in terms of its projection. If you have the benefit of being able to observe multiple different species of emission lines, you can use those all together to allow you to get a better classification than you would with any one individual system. So far I've been cheating a little bit, and I told you early on that MaNGA had a full spectral resolution of about 2,000 or so, and I've been cheerfully telling you what it can tell us about velocity dispersions of 20 kilometers a second. And you might have been asking yourself how I'm able to get away with that, or maybe I was able to just skip over that detail entirely. The problem is that if you're trying to do velocities of 20 kilometers a second with a spectrograph that has a 70 kilometer a second instrumental resolution, that's a very non-trivial thing to do. We're not only working below the spectral resolution, we're working substantially below the spectral resolution. Likewise, I showed you a picture of our instrument. It was a Cassegrain-mounted spectrograph. It's just going to be flopping around all of those fibers in time on the back of a telescope with the gravity vector changing all the time. So I can show you what a spectral resolution looks like. It's roughly 70 kilometers a second on average. We got up to 50 or so in some cases, 90 in the worst cases, but there's a spread about that depending on which fiber you look like. And even within a given IFU, spectral resolutions can change. Here's a couple examples, for instance. This one's fairly constant, but this one, we're getting a difference of about 20% in effective spectral resolution just over the field of view of that IFU. Effectively, our spectral resolution changes both with wavelength, with position, and temporally as well within a given observation. And yet I'm telling you that we can do 20 kilometer a second velocities. The reason why is because it's possible to do that kind of science far below the spectral resolution with enough work and enough understanding of exactly what the characteristics of your instrument are. So on the left here, I'm showing you just a couple schematic examples. A 70 kilometer line spread function is shown in that black line there. A 20 kilometer a second science signal convolved with that gives you the red line, which is almost impossible to distinguish between them, but it is possible with enough statistics. It's a lot easier by the time you get out to the blue, 70 kilometers a second, and that gives rise to the traditional wisdom that you don't do science below the spectral resolution because it's a lot easier to disentangle the actual science signal from your instrument. However, with sufficient knowledge of your line spread function, the systematic uncertainties are small. In particular, to do this kind of observation, we need to know our line spread function to within 1% for everywhere in the IFU, for every fiber, and for every individual exposure that it changes between. With enough signal to noise, your statistical uncertainties are small. So any individual measurement you make for any one observation is going to have some large uncertainties, but the ensemble of many such measurements can still be very accurate. So we need to know our line spread function to better than 1% for every spaxel, which is what we do. We get down to a 0.5% knowledge of our spectral line resolution after many years of effort attempting to do this throughout the survey, measuring very carefully from our observations of reference sources and dealing with a lot of other effects as well. We need to deal with the fact that our line spread function is critically sampled, so dealing with issues like the pixel phase that a line occurs at, how you resample those spectra. It all becomes extremely important when you want to get this to this kind of a level. But by the time we reach the end of the survey, we could look at higher resolution spectroscopic studies of a smaller number of galaxies and convince ourselves that we were doing the right thing. So on the left here, I'm showing you a couple histograms of what we got for our velocity dispersions for a few galaxies in common with two much higher spectral resolution surveys. One was the disk mass survey, of about 10,000 or so, for a factor of 5 higher spectral resolution, and also a few from the SAMI survey. SAMI was in the south, we were in the north. There wasn't a great deal of overlap between the surveys, but there were enough galaxies to be able to make this comparison. And we could say in early versions of our data reduction, we kind of missed the mark. Our velocity dispersions weren't really where they needed to be. But as we continued to learn more information about the system, as we continued to study the effects of sampling in more detail, we were able to bring those histograms into alignment and say that we were getting the same velocity dispersions for the same spaxels as these higher resolution surveys. That's kind of made a little bit more forcefully by this plot here, where I'm showing you one galaxy that we observed in our survey and was also observed in the SAMI survey in a version of that survey that had twice as high spectral resolution. Showing you the H-alpha flux on the left. The MaNGA field of view is bigger in this case, so it extends beyond the SAMI field of view. The velocity map and the velocity dispersion map. And I should note that these are two completely different instruments on different telescopes in different hemispheres, reduced with a data pipeline written by different people. And they still match just as well. I'd never dreamed when I looked at the MaNGA maps originally that that little nubbin above and below the central core, for instance, was a real feature in the velocity dispersion. But it is. You see it in both of these maps and gives us a large amount of confidence that when we are measuring a velocity dispersion with MaNGA, we are now at the point where we can really believe that velocity dispersion and are able to do science that is well beyond the nominal spectral resolution of our instrument because we've studied the instrument so far. That means we can make plots like this one. So here I'm showing you a plot of the relation between the H-alpha velocity dispersion in these disks as a function of the star formation rate in the galaxies. This is a plot I spent a lot of time looking at for the high redshift universe. And kind of my original goal getting into all of this work was to make this plot for MaNGA. What does the local universe look like? What is the relation between the star formation properties of a galaxy and the velocity dispersion, the kinematics that you see in that galaxy? Now we can fill this in with northwards of 1 million star-forming galaxies and star-forming spaxels in about 4,500 galaxies, corrected for survival bias, which I won't go into, but I'm happy to talk about if anybody wants to know what I mean by survival bias with well below the spectral resolution. And we can observe these well-defined trends, where if you look at galaxies that are higher star formation rate, or alternatively have higher star formation rate surface density, they're the ones that have higher velocity dispersion. By and large, this is telling us what we already knew from smaller surveys, but now with a factor of 100 or so times greater statistics. Namely, as you go up from low star formation rates of less than solar mass per year, 0.01, 0.1, you go from velocity dispersions of about 18 kilometers a second up to about 30 kilometers a second by the time you go over a star formation rate of a stellar mass per year. That trend continues to higher star formation rates and star formation rate surface densities until you observe large velocity dispersions by the time you observe starburst galaxies in the distant universe. So we filled in this plot with much greater statistics than ever before, but so far this is nothing that we didn't know when we started MaNGA. What makes us different is that we can use those statistics now to ask why this trend occurs and whether or not we can slice and dice that to learn more about what's actually going on in these galaxies. So the first thing we can do is ask, okay, is this a trend with star formation rate or stellar mass? If you make this plot of how velocity dispersions depend on star formation rate and stellar mass, you'll observe a correlation with both. People have done both in the past, and it's always been argued about which one's the actual driver. Star formation rate and stellar mass themselves are, of course, strongly correlated on the star formation main sequence. Here's a plot of star formation rate and stellar mass in all the MaNGA galaxies, for instance. Obviously, the more star-forming ones tend to be the more massive galaxies within this sequence. We can now break that degeneracy with subsets and say that we see a very strong trend against star formation rate for many different bins in stellar mass. But the same is not true for stellar mass. If you look at the trends with mass and break it down into bins of star formation rate, the trend disappears. It's telling you that the primary relation is star formation rate, and any correlations with mass are just due to the correlation between those later two quantities. We're starting to try and tease out the correlations that are just induced and try and get at what the primary underlying correlations are instead. We can do the same kind of thing with star formation rate surface density. I showed you two versions of the plot a couple of slides ago, with a relation both with the total star formation rate of a galaxy and with the star formation rate surface density. What we'd anticipated going in is it's the surface density that matters. As you have more star formation rate in a given small region within a galaxy, it injects more feedback into the surrounding gas and it puffs up the velocity dispersion accordingly. And that's not what we observed. Instead, if you try making this plot, so local velocity dispersion against localized star formation rate surface density, you see this trend we've been looking at. But if you break it down into different star formation rate bins, you can see the trend disappears, and it's dominated just by the offsets in star formation rate across that region. What it's telling us is that the ionized gas turbulence in these galaxies is driven by a global galaxy property, not local feedback variations within the individual galaxy itself. Is that global property actually star formation rate? Not necessarily. We know it's not stellar mass. One possibility is it could be the total molecular gas mass of the galaxy that we're looking at. If you've got a higher molecular gas mass, that could give you a higher midplane gas pressure, which gives rise to a larger velocity dispersion between individual star-forming regions. That's what we're observing. We're now able to ask that question, whereas previously we didn't even know that we needed to be looking in that area. You can do a variety of other more complicated things as well. I won't go into this plot in too much detail, but the rough idea behind it is that if you look at the line of sight velocity dispersion as a function of the inclination of the galaxy, there shouldn't be a trend. Galaxies don't care where we are, they don't care how we see them, they shouldn't have different velocity dispersions if you see them face on or edge on. If you see any differences, that's telling you something about intrinsic differences due to the projection effect. What you can do with this is you can start teasing out differences between the disk vertical velocity dispersion and the dispersions in the radial and azimuthal directions as well. So you can start to understand in an ensemble sense for a large sample of the entire main sequence of star-forming galaxies, what is the typical velocity dispersion ellipsoid? What is the dispersion of gas in all three different dimensions within galaxies? And we come up with answers that seem more or less reasonable based on observations within the Milky Way. The Milky Way itself might not be fully average, but it might not be too far away from average either. We can do other things as well. We've got multiple different lines, so we don't just need to look at, say, H alpha, O2, S2. We can look at all of them. So if you look within a given star-forming region, a given H2 region, where you see different lines within those H2 regions is a product of how hard those lines are to ionize. So I'm showing you here a list of the ionization potentials for different lines. Many of them, so things like O2, N2, S2, all have ionization properties that are pretty similar to hydrogen. So when you see the emission from those kinds of elements, they're coming from a comparable region in the nebula. O3 is harder to ionize, so it'll tend to occur deeper in the nebula. Here, for instance, I'm showing you a plot of a few different metallicities. So if you look deeper in the nebula, that's where you tend to get this doubly ionized oxygen emission. As you look further and further out, then you might get the singly ionized oxygen emission. Then right at the very edge, you get the neutral emission from oxygen as well. So depending on which line you look at, you're probing to different depths within these H2 regions. That hangs together with what we're observing for the velocity dispersions as well. We can say if you look at the species of all of the things that you'd expect to be similar, N2, S2, O2, those are all pretty comparable to one another. So this is the ratio between the velocity dispersions we get from those lines to what we get from H alpha, and more or less they're all about the same throughout this entire sequence of star formation rates. As you look at O3 though, this is something that's harder to ionize, it lives deeper within those individual H2 regions. It starts to depart from that trend by the time you go down to low star formation rates and low velocity dispersions, suggesting when you're looking in this region, you're starting to be dominated more by the physics internal to the H2 regions themselves, as opposed to at the high end, where you're dominated more by the distribution of these H2 regions. Working together with that, we get the O1 velocity dispersions. These are the very edges of the H2 nebulae. They also tend to be rather higher than all of the others based on what the typical velocity trends are within individual H2 regions. Statistics are getting pretty bad for these observations, even for MaNGA, because there's a very limited number of galaxies with O1 sufficiently bright that we can measure it in order to be able to do this measurement. But it kind of hangs together with this general picture that we're looking at. And finally, we can try and do the real Hail Mary of these observations and say, can we do molecular gas physics with an R of 2000 spectrograph and 70 kilometer a second line spread function? And generally we're finding that even though it's getting a little dicey at this point, we can get reasonable results even by the time you get down to this level. So if you take the trends I've shown you before and convert that to a molecular mass surface brightness, and you try folding out things from the actual H2 region physics themselves, assume some characteristic velocity dispersion for the H2 regions, the H2 region expansion, you can subtract that out and look at the distribution or velocity dispersion between the individual H2 regions, tracing the molecular gas within the disk, and ask what the dispersion is between those H2 regions and how that behaves with molecular gas surface brightness. And you can find this kind of trend here in black, where you dip down from about 30 kilometers a second dispersion at the highest molecular gas surface brightnesses down to about 5 kilometers a second by the time you get to the lowest star-forming systems. And in orange, I'm showing you what we get with ALMA. Well, not we, a completely different group. But by and large, the two results hang together. We're getting comparable results for what's going on with the molecular gas, even when we're looking at the ionized gas with sufficient understanding of the individual pieces of physics going into it. So, that was MaNGA, a very small, tiny snippet of one particular part of science that I was interested in doing with it. Now, MaNGA, of course, was a very large collaboration. It was going for many years, and people have written hundreds of papers with it on lots of different topics that I am completely neglecting, and if you're interested, I'd encourage you to look them up in future. But for the last few minutes, what I'd like to do is something completely different and shift to a little bit of JWST data, just because it's impossible for me to give a talk anymore without talking at least a little bit about JWST. I'm also going to completely shift science topics now. I've been talking about galaxies, now I'm going to turn to talking about massive stars, because, well, life would be boring if you only ever studied just one thing. One of the things we've been looking at with JWST is the bright star 10 Lac. So this is a 09 star that we observed for purposes of calibration in MIRI early on. And it's really one of the prototype galaxies for the 09 type. It's a fifth magnitude star. Nonetheless, we stared at it for 3 hours with JWST, which is something that ordinarily you wouldn't ever be able to get approved to do. But because of its calibration program, we could do crazy things you might not ordinarily be able to get approved to do. Here's an image of what the star itself looks like. It looks like a point source. There's not much of interest around it, and it is good for measuring the point spread function of the instrument. By and large, it, or as hoped, has a relatively featureless spectrum. It's got some hydrogen and helium lines in there, but by and large, it's well behaved. It was good in terms of being able to use it for flux calibration. And for a couple of years, it really pinned down the flux calibration of the MOS on JWST. We've moved on now. We're building other stars into the sequence as well. One of the things that bothered me for a while was that it was just some weird square notches in the spectrum that I assumed were from some weird aspect of the calibration that we'd done that I was interpolating over when we got our flux calibrations. When we dug more into it, though, we realized those notches weren't, in fact, weird calibration artifacts at all, but we are, in fact, seeing very broad, high ionized emission in 10 lac. We're seeing 2,000 kilometers a second wide neon 5, neon 6, and O4 emission. This is very hot 100 eV, highly ionized radiation coming off of the star, making these wide features. They effectively look like things that you've observed in Wolf-Rayet stars, except that we never expected to see these in a typical O9 type star. Turns out this is interesting because the significant mass outflow that's represented by these very broad winds can actually resolve some of the main outstanding problems with understanding why we saw very weak winds in such stars before. This is based on observations in the UV and optical. And the answer to the question is because there are no lines in the UV and the optical. The density and the temperature in these features is sufficient such that if you want to see the outflows, you just have to look in the mid-infrared. You have to have deep mid-infrared spectra such as people have never had before. And now that we're able to look for such things, we've opened up a new region of the observational parameter space, and we can see new things we didn't expect to have there. This is just one object, but we're following up with, now that we know it's there and to look for it, a much larger sample of observations as well, a larger number of O stars. And so hopefully in the near future, I'll be able to tell you a proper colloquium, not just 5 minutes crammed at the end of a completely unrelated topic, in terms of what this might mean for the oxygen, for the late O-type sample. So I will end there just with a few key takeaways. First, IFUs are extraordinarily powerful tools, as are statistics of large samples. And it is incredibly important to know your instrument. If you know your instrument well, you know how it behaves, you know all of its quirks, you know all of the instrumental properties and how they vary, you can unlock entirely new areas of science that you've really no right to be able to do with the instrument that you've got. You can do spectral resolution 10,000 science with an R of 2,000 spectrograph if you understand your instrument well enough. Likewise, if you try looking at the kinematics of galaxies, that can help you revise your understanding of what's going on with the sources that ionize the gas in those galaxies. And we can break down that there's a strong relation, as I showed you, between the H-alpha velocity dispersion and the galaxy star formation rate, and we can say that that's driven by some global property of the galaxy, not the localized star formation rate as we'd always assumed. And finally, JWST is cool. It's showing us new things all the time. And I hope to be able to tell you more about it in future. So, thank you.
All right. Thanks a lot, David. This was extremely interesting, and I think you overestimated our knowledge about galaxies, because here we do a lot of stellar evolution, which is, as you mentioned, like just a single point source. And so for us, it's always very exciting to have also different talks that cover also the wider aspect. And I didn't give an introduction because we started a little bit late, but I would also like to say that David mentioned about being bored when you work only on one thing. I would like to point out that David does leatherworking, stained glass work, also historical fencing, or was it?
Not in a few years, but yes.
Not in a few years. So if you would like to talk about any of these hobbies of David's, be welcome to do so during the lunch break. And we have a bit of time for questions. So I would like to first give the floor to the audience, and then I have a few of my own. I don't know if people feel, yeah, I'll just run up.
Hello. I have a question about the inclination of the galaxies, because I would expect that edge-on galaxies are a bit more tricky to analyze, because we know that for the Milky Way, especially your analysis is indivisible and up to 1 micron, I think I've seen. And we know that we have these clouds that are hiding parts of the galactic center for the Milky Way. So how are you sure that you can compare the results for edge-on galaxies with all the other galaxies?
So I should say we don't go to the purely edge-on galaxies for the reasons that you say. If you're looking at something that is exactly edge-on, it's really hard to make much of a measurement at all. Really, the lowest we go is an inclination of about 20 to 25 degrees or so, which is still enough that you can see at least in over the top of the disk. You can start to see some of the more radial and azimuthal type effects coming in. But no, you're right, there is going to be a limit to how far you can go. Likewise, we tend to block off the very central part of the galaxy from our analysis just because the beam of the telescope is smearing things sufficiently that it's hard to get a reasonable measurement there. We make a correction for what we expect that beam smearing to be across all the various different parts of the galaxy. And we pull different pieces off the major axis and the minor axis of the galaxy to try to do that analysis. I guess I'm saying, yes, you're right, it's hard, and we don't do the very lowest inclinations for that reason.
Okay, thank you. And then another question was like, why did you stop at 1 microns? I understand there's like some technical reasons, but would there be a scientific advantage of having the data for more in the infrared?
I agree entirely. And all I can say is that we were driven by the fact we used an existing instrument. So we did not, in fact, build our own spectrograph at all. The BOSS survey originally built the spectrographs only go out to a micron or so because that's all they needed for the science purposes of that survey. We pick up a few S3 lines right at the very long wavelength end of 9,900 angstroms or so. There's a faint excuse me, a faint feature that can be tied to what the IMF is in a few stars that we just barely pick up at the very longest red end as well. We were able to do a few papers trying to look at and see what that would tell us for the initial mass function in galaxies. But if we were able to build our own spectrograph, yes, we would have gone beyond a micron. And in fact, what I didn't talk at all about today is what came after MaNGA. So with the successes of MaNGA, then for the current generation of the Sloan 5 survey, we actually built a new project called the Local Volume Mapper, which is taking MaNGA kind of to the extreme. Integral field units that cover a significant fraction of a degree on the sky and are being used to map half of the Milky Way, the Magellanic Clouds, and those we were able to design to our own spec, build our own instruments based off of the DESI spectrographs, and those do go out beyond a micron. Yeah.
Okay, thank you.
Any other questions in the room?
Hey David, thanks for your lovely talk. So about the 10 lakh, because I know we had the discussion of why the SNR of my data seems a lot different from the SNR of the observation at the start after commissioning. Is there any observed variability, or does it seem very constant? Or is the SNR of my observations just really preventing you from seeing the difference?
As best as we can tell, it seems to be fairly constant. To catch everybody else up, then there have been two different very long observations of 10 lakh that we've taken now. The ones that I was showing you a moment ago was based on a 57-point scan of 10 lakh over the field of view that we used to derive the distortion calibration. Take a bright star, put it in many different locations, see how it moves. You can reconstruct your distortion solution from it. The other deep one is from Danny's program, where we've done a fine raster scan around a few key locations that is actually a deeper program but has worse signal to noise when you stack all the data together. And we believe that's because of uncertainties in our flat fielding. Because many of the observations for the second program are taken with only teeny tiny little dithers off the same location, they're probing effectively the same pixels, and so any flat field uncertainties won't be washed out as they will when you're putting it at many locations throughout the field of view. As best we can tell within the signal to noise, though, there's an obvious trend in terms of the evolution of the system.
All right, thanks. Any other questions? Otherwise, I'll have two for you. Okay. I was wondering, the first question I had was regarding the age determination that you mentioned for the galactic populations, and you mentioned quickly that that's based on the width of the H alpha line. But here, well, when we talk about ages, we talk about ages of stars, if they're young stellar objects, if they're asymptotic giant branch, etc. So I was trying to understand, are you mainly interested in the H-alpha properties and you limit to that, or do you also then try to, using the stellar models that you showed and potentially some isochrones, I guess, for main sequence stars, do you then also produce results based on your data and how what the model tells you for the stellar ages across the HR diagram?
Right, so there's a lot of information packed into that. Focusing on age specifically, I haven't been using age estimates myself for anything large in terms of my analysis. It's more comparing to it and seeing what information you could get from it. One of the things you can do from the analysis of the MaNGA data is you can do full spectral modeling. You use your information about stellar populations, you model what's going on with the stellar continuum. That tells you what kind of a mix of old and young population stars you have in there. Along with the emission lines, it tells you something about the young stars. So there's kind of two rough ways of estimating the age of a stellar population based on these spectra. The first is the H-alpha equivalent width. This is really just the ratio of what is the strength of the bright emission lines from the young population compared to the strength of the stellar continuum from the old population. The second way of doing it is just by looking at what is the strength of the 4,000 angstrom break, which tells you something about the population of A-type stars in the spectrum. Those both correlate very well with the age of a system, although, of course, translating that to specific megayears is an area that people argue over constantly.
Thank you. And then the second question I had was regarding cross-calibration between the different surveys. So in general, I would understand you observe some standard spectrophotometric stars that we have models for, etc. But I was wondering, now you showed, for instance, the case of MaNGA versus AMI. So do you have specific targets you try to hook on and then basically compare all the other galactic properties based on that? Or I'm just trying to wrap my head around such surveys and how, let's say, fiber-fed spectrographs can get cross-calibrated across different parts of the Earth, as it were.
In large part, it's based on luck. There weren't any deliberately targeted observations in common. MaNGA and SAMI, for instance, were based in different hemispheres, had slightly different optimizations. We both had a similar set of galaxies in equatorial strips that we attempted to do some in common, which worked out better or worse. There were about 30 or so in both surveys in the end of things that we could use for that overlap. Likewise, there were a number of observations from the disk mass survey, things that we put in the MaNGA sample specifically to follow up those galaxies. We had the disk mass folks on our team. There was science they wanted to do with those galaxies, so we followed them up. That was part of why we had that overlap. We have actually since then followed up more deliberately a set of MaNGA galaxies with R of 10,000 spectroscopy from other instruments, explicitly to say how good a job that we did with the spectral resolution calibration and see, did we actually do a good job? Are all of these results meaningful? What that later exercise has told us is, we might have been out by a kilometer a second or so. When I tell you 20 kilometers a second, maybe it's 19. I'll take that.
Very exciting.
We've also tried to do lots of cross-calibration against other things as well. There are a number of stars observed with X-shooters, say, that we could compare to our stellar library. It's really a mix and match between various different things.
Gotcha. And what's next then for the? It's not really quick. What's next for the next for the MaNGA survey? Are you continuing? Is there now with the LVM, as you mentioned, you plan to add additional data that might help. Maybe MaNGA is more of a niche than instrument to add more time to complement, let's say, what LVM will be doing.
Yeah, so MaNGA itself is now done. It's disassembled. The units themselves no longer exist. It, however, did feed into the LVM survey in terms of the technical knowledge and how to build these instruments. That's now following up with much finer scales. Now, MaNGA's beam is about a kiloparsec or so in galaxies. LVM is following up more at the 10 parsec scale in a much smaller number of galaxies, the Milky Way and local group. But of course at a much larger scale across the entire galaxy. I know that SAMI is looking into a scaled-up version of their own survey where, last I heard, they wanted to do 100,000 or 200,000 galaxies. Honestly, I don't know how that's going. as such things go. I just got to the point where the MaNGA survey was done. I finally managed to do the science that got me involved in the survey to begin with, and then we launched JWST. And
Perfect.
that has been a large fraction of my time ever since then. We're, of course, doing similar things using JWST with high redshift galaxies going forward. But
Yeah, that's
been the main focus of things lately.
Yeah. All right. Thanks a lot, David. And I think we'll close it here.
Cheers.
Yeah.